properties of carbon. So we talked about water as an important thing in life, right? The whole chapter was just set aside for water. And you saw all the wonderful properties, and you did the experiment to go with it. So you see how that's, in order to see, like planets, you've got to see some sort of, from our understanding of life on Earth, if we see some sort of discovery of water on other planets, or some remnant of water on other planets, and there's a possibility that life is on there. Well, carbon is our other flip side of that whole thing. Carbon is the basis of organic chemistry. And life does not exist unless we have carbon. All the proteins and fats that are part of you, and carbohydrates or sugars, you are a carbon. About 18% of your weight is carbon. So although cells are 70-90% water, as I mentioned, like I said, 18% of your body weight is related to carbon. And that's one of the four major elements in our body. It's the most versatile element that we use on Earth. It's neat. It's got 4 valence electrons in its shell. That means it could have 4 bonds to it. And putting 4 bonds to this is wonderful. We could put hydrogens and oxygens, and you'll see where this comes. Okay? So the formation of carbon-carbon bonds was this important discovery to realize that life came from simple things and became more complex. So there was this, we're going back, we do a little history. There's this guy, Stanley Miller, back in 1953, and he proposed this hypothesis, this question. And he said, can simple molecules and kinetic energy and motion, lead to chemical evolution? Can you take simple things and maybe with electricity, can they turn into something more complex, i.e. life? So that's what he proposed. And he tried to come up with an experiment. And if he didn't prove it, then we call it a null hypothesis. If this doesn't work, then chemical evolution will not occur even with an input of energy. We call that a null hypothesis if the hypothesis does not prove it. So he made a prediction, right? Doing the scientific method. He made a prediction that complex organic compounds, anything with carbon, will be found in liquid water. And the null hypothesis, or the prediction of it, would be only the starting molecules to be found in the liquid water. So if you put simple molecules in liquid water, put electricity into it, then we have different, bigger molecules forming. Or the electricity and storms do nothing, and we have the same molecules before and after the whole situation. That's what he proposed. So he made this experiment. He took water, the sea, and in the sea, in the ocean, all that water, there's a lot of chemicals in there, right? It's not distilled water. There's a lot of different molecules and things. I'm not talking about life. I'm just talking about like calcium. There's a lot of different things in there. If you boil this, then the chemicals in the water will go up in the air. And in fact, 4 billion years ago, that's all there was just water. And there will be all these water vapors going into the air, but there was years and decades of storms going on. Lightning and thunder. And that electricity in the air was changing things with molecules in the air that just evaporated from the ocean. And he did this experiment where this goes in, and some of the things in the water vapor were methane gas, which is really just C4 or CH4. So it's C. So methane gas is the simplest form of a carbon molecule. It's really just CH4, which looks like this. So is there something with electricity that a bunch of these methane gases, can they combine to each other? Can they form other things with nitrogen and oxygen that's also in the air? And that's what he did, because there was also ammonia in there, ammonia gas, which is NH3. So they're mixing all this up with electricity. And then it came down as rain, it condensed, and went back into the ocean. Goes right back into the ocean. He had this little thing here that as it was going back in the ocean, he could collect some of that stuff before it goes into the ocean and test it. Does the experiment make sense, what was going on here? Okay, before we go further. So the results is that he actually saw other things being formed in there. Bigger, complex things. We could have glycine in there. See carbons with two that came together. We had formaldehyde in there, where carbons combined with oxygen. New things started happening. So his conclusion was that chemical evolution occurs readily if simple molecules with high free energy, right, kinetic energy, the electricity and stuff, are exposed to a source of this kinetic energy. That's a pretty fascinating thing. Okay? And that's what started the whole thing, our realizing that that's what happened probably years ago, decades, billions of years ago, right? Questions about that? So let's talk about organic compounds. All right? Organic chemistry. Anything with carbon, with a couple exceptions, anything with carbon is organic chemistry. Okay? It forms almost an unlimited array of different molecules. You can make carbons being strung together in one strand like a chain. You could put them in rings. You could put them, you can do a lot of things with it. You can make them flat structures and so forth. All right? And it's used, like I said, one carbon, you could actually have 4 bonds to it. So you could have a double bond there, and you could have a couple single bonds. You could have 4 single bonds. So you could create these more complex things. Okay? So carbon binding with hydrogen, oxygen, nitrogen, phosphorus, and sulfur, make it more complex. Those are what carbon usually will bind to. Okay? Along with itself, a carbon to a carbon. Now, inorganic chemistry is anything without carbon. Simple as that. Okay? Water is the most abundant and most important inorganic compound in all living things, as we just mentioned with the whole chapter. The only 2 exceptions is bicarb, which we've been showing you about with the carbonic anhydrous reaction, and carbon dioxide. And I'm not too sure why they consider, maybe Dr. Kamo, do you know why we don't consider bicarb and carbon dioxide organic? Does it have something to do with the polarity? I'm not too sure.
Well, normally, if it's organic, it's usually carb with a hydrogen.
Yeah.
Why bicarb is that way? I'm not
Yeah,
really sure.
we're not too sure. So when you take chemistry, this is in a chemistry class, when you take chemistry, I'm sure they're going to explain that more. So I won't ask you why. Just put in the back of your head that bicarbonate ions and carbon dioxide are two things that have carbon that are not considered organic. These are considered inorganic. Okay? I think it has something to do with the polarity. Okay, the way it works. Okay, clear with that? All right, but everything else with carbon, it's organic. No question about it. Okay, so these are just balances. You can look at this on your own. It's just the balances of the major elements that we deal with, right? That's this carbon, nitrogen, oxygen, and hydrogen. Okay, just so you can see that, and the balances are there. So you can see here on the carbon, it only has 4 valences, and how many, or 4 valence electrons, and how many valence electrons do you need in the outer shell to become stable? 8. Good. Okay, so that means it combined with 4. It can make 4 different bonds. This is urea. It's an organic compound found in urine in many animals. I will never ask you to draw out compounds. You do need to recognize them. You won't have to recognize urea, but I'm going to show you a few that you do have to recognize. All right? But that's just showing you how things get combined. You can see the carbon there is bound by 4 bonds, even including a double bond. Okay? But when carbon has single bonds, it creates more of a tetrahedral structure. Kind of looks like this. Okay? And there's the carbon, and there's a bond right there, a single bond. So the way these are sticking out is more of a 3-dimensional thing, because there's 3 hydrogens over here. But I want you to also understand, too, that this carbon can swirl and rotate along this one axis, right? If I have this, if I have something over here, it'll spin. If this is there's a carbon here, so if there's a carbon here and a carbon over here, and this is the single bond, then this carbon can turn around here, right? It's only on one. It can turn around here. And that's going to introduce us to, if there's a nitrogen here and a hydrogen up there, things can swirl around. You'll see what I'm talking about. Now, with a double bond, they create more of a flattened structure. So here's the 2 carbons with a double bond. You could put 2 hydrogens here. You can put a third, because then this carbon would have 1, 2, 3, 4, and then the other one would be 5 bonds. You can't do that. But look what happens with this. When there's a double bond there, so if I had another stick over here and the carbon was on the 2 sticks, you can't turn that, correct? Does that make sense? There's no axle. It can't really turn because another thing is blocking it from turning. So that means that if there's a hydrogen here and a nitrogen here, that's the way it is. But I could put the nitrogen up here and the hydrogen down here. It creates different structures. I'm going to show you what I mean. They're called isomers. So this is, again, just trying to show you in different forms. This is called molecular form, structure, ball and stick, which I'm going to try and make a few for you, and in space-filling models. But you can see this one here, the ethane. This was the 2 carbons with 1 single bond in it. Well, you can see here, right? 2 carbons and 1 single bond. This carbon can swirl on that single bond. This carbon can swirl on that, rotate on its single bond. So it doesn't matter what these are. However, on this, there's a double bond here. This is ethene or ethylene. And it can't swirl. So you could have a nitrogen here and a nitrogen here, or you can have a nitrogen here or a nitrogen here. Those are 2 different structures. They can either be on both on the bottom, or one could be on the bottom, one could be on the top. And that will, as I mentioned to you before, that function reflects structure. That because of where they are and they can't move, it's either going to do something good, something bad, or something just not at all. So it's the way something is made or structured that defines what it's going to do. So we have carbon skeletons, carbon chains that form these structures, okay? They could vary in length. They could be branched. They could be in rings, as I mentioned. And I'm going to show you examples of this. We have hydrocarbons. And hydrocarbons is basically a carbon that's going to be bound to a hydrogen, as you just saw in the previous slides. Many organic molecules, such as fats and lipids, have many hydrogen-carbon components to them. Okay? And hydrocarbons, what's good about them is that they undergo a lot of different reactions. The reason why that Snickers bar is so good for you is to entice you to eat it, to put it in your body, and your body will change it into energy. Okay? So this is just showing you some pictures, right? Here's the ethane gas that we kind of showed you before with the two carbons there. But you can also appreciate the hydrocarbons, right? Hydrogen's bound to carbons. Propane, right? Now we're going to some sort of gas. So the more carbons becomes a little bit more, well, not solid, but liquids, right? Butane gas, right? To do lighters and stuff, it's gas. Oh, no, that's liquid. That's liquid, right? Butane is liquid. So octane is really liquid, right? Octane is what you fill up your cars with. Oct means 8, so that means there's 8 carbons there. So the more carbons becomes from gas going into liquid. All right, and here's some showing some double bonds in here. You can also see that some of them are starting to branch. So you can branch. Or you can put them in rings. There's a lot of different structures that we're going to see with this. These are fats, or lipids. All right, we'll talk about it later. But you can see they could be really long chains over here of carbons. Also notice that if there's a double bond, it bends. And that's an important fact that we're going to talk about to define between a saturated and unsaturated fat. But I don't want you to think they're only going to be like 2 or 3 carbons together. They could be like 23, 40 carbons, really long.